my habit is that I always like to play a song before the lecture, and I try to correlate the song with the lecture or something that we have that we experienced recently. So I wonder if any of you can guess why am I playing the song "Fly Me to the Moon" for today? Anyone want to make a guess? Quick guess. Okay, so looks like there's no one really understand what I'm thinking about, which is pretty sad. So the main reason why I'm playing this song is because I'm not sure how many of you watched the news in yesterday, right? So NASA apparently have a perseverance on landing on Mars yesterday and start, well, probably not yesterday, but at least that's the first time we saw videos from the red planet, the first time in human history, right? So if you paid attention to the lyrics that in the "Fly Me to the Moon," and this is spring season, right? And there's a sentence saying that like, let me see what spring is like on Jupiter and Mars, right? So that's why I'm playing this song. And also it's also interesting that what we are going to talk about today is somewhat related to to perseverance landing on Mars. So what I'm going to share with you is you can see this one, right? So from what you can see is that well, this is the robot that NASA used to roll over on Mars, and as you can see, the storage they are using is something called flash memory. And today, the lecture we are going to talk about is related to this. So so our lecture today is very important in a way that it's not only related to the file system, but also related to you know, a lot of different things. So, but before we start, it's always a good idea that we should talk about what's the stuff we are going to talk where we are coming from. So we mentioned that in the operating system we have different abstractions, processes for the whole volume machine, the thread for the processor abstraction, and the virtual memory for the abstraction of memory, and file system for the abstraction of storage and everything else, right? So that's the main idea. And for example, if you want, and to facilitate this abstraction, the Unix start to introduce the idea of file system. So everything is actually under the umbrella of file system. So if you have a hard disk drive, the way how your request reaches hard disk drive is that you still use, no matter what kind of hard disk drive you are using, no matter what kind of storage device that you are using, you use fread write, fopen, fclose to manipulate with your device, and your library will translate your request to file system request in a way that we use this file name to look up for their block addresses on the device, and use these addresses and the commands that your driver accepts. For example, IO kernel interface, and then forward this command to your device driver, and finally the device controller will translate them to the exact electrical signals. So that's how you reach the hard disk drive. However, the file system is not just like that, because there are a lot of things you have to care about. The abstraction is good, but if you want to make the abstraction efficient, that actually needs a lot of work. So one of the paper we read in the last week is the fast file system. It improved the spread out the data location through cylinder groups, and it tried to improve the bandwidth and support larger files from using larger blocks. However, with larger blocks, you are going to see a lot of internal fragments. So that's why they introduced the idea of fragments. And they also have allocators to address what's the best usage of your cylinder group and blocks within the cylinder group, and as well as other new features that people want. However, as you learn, the fast file system still has its own drawback in a way that the write performance is not as great as read performance, although it's faster than the fast file system already. But people are greedy, and in the past, people don't think that the write performance is so critical because if you are on a supercomputer, or even now, if your main workload is high performance computing, most of the time you are reading larger amount of data and you perform a lot of data analytics on these larger files, and in comparing with the data that you read, the number of writes is actually relatively small. However, that's just for the supercomputer. If you move your scenario to personal computers, to everyday computer, to workstations, and as also if the computer has larger enough memory, turns out that the write traffic is dominating, especially those write traffic to small files. So the UFS, the fast file system published in 1984, talking about the optimization for large files doesn't necessarily accommodate the demand of the computer that you use every day. And there is a huge gap between sequential access and random access in the device design. So conventional file systems that cannot accommodate those. So the basic idea of log structure file system is we buffer changes in the system in the main memory and commit those changes sequentially to the disk with fluid amount of write operation, meaning that we aggregate those changes and write them together. So your writes will, although they are small writes, but when you aggregate them together in the main memory and only committed once, so it's actually implementing the idea like page clustering, but instead for virtual memory content, they are using it for file system content. In this way, you can reduce the number of writes, plus every time you write is a larger chunk writes. So that's what the log file system proposed. So if you see this animation, which I spent a lot of time talking about, the log structure file system in motion is like this. You aggregate your writes in a write buffer, and then instead of writing each small pieces of the chunk to the disk, you write them all at once. And after you written this data in the disk space, you create an inode just right next to it. So your inode is very close to where your data is. And another good thing about that is that, well, you only eliminate the buffered copy once you are 100% for sure this inode has been updated. And after that, your inode map will create a link to that. And again, you might think about the inode map is another access, but the log structure file system, they can actually cache this in the files in the main memory. And if you have the second chunk, you just keep appending to the end of your log structure file system free space. And in the meantime, you don't have to erase anything. And even though you are going to update the original data chunk one, you just keep appending to the end. And you can also merge your change to a new data to the new data chunk, and then commit it once to this new place and create a new inode. And the good thing about this is that if this update failed, at least you have this version that you can work with and can restart from. So so log structure file system actually is a pretty good idea in terms of crash recovery, because you always have an older copy in your system. And it's also good if your hardware failure in the middle, because all you need to do is to retry, because you still have a copy in the write buffer before your writes are successfully committed. So that's the idea of log structure file system. And however, as you could imagine, when you keep running this log structure file system, you are going to create a lot of invalid copies in your system. So definitely you need garbage collection to move data around and make sure that you always have enough space on enough contiguous segments on the disk for you to keep writing. So, so as a summary of the lessons we learned, right? So performance is closely related to the underlying architecture. So the old UFS, it performs pretty poor on hard disk drive because it ignores the nature of hard disk drive. And fast file system, they try to allocate data to consider locality on the disk access to minimize the latencies. However, also the workload changes and other hardware changes also affect the design philosophy of your software. So for example, fast file system is mainly optimized for reads as well as large file accesses. And log structure file system is optimized for writes and small data accesses. So they are pretty different. And the reason why log structure file system thinking that's a more important issue because the architecture changes. You have faster processor, you have larger memory now, right? So that's the lesson you learn, right? The file system, the design philosophy should change all the time whenever your hardware changes, whenever your software workload changes. So if you are sticking with what the textbook is always telling you, this is good, this is good, this is the best policy, you are not going to be the top performing software architect or a system designer because you are very likely to ignore what the real world demand looks like. And one thing that you have to learn is that always pay attention to what's happening surrounding. So today, before we are going to talk about flash memory because, as we mentioned, the underlying architecture change would affect the way how you design your file system as well as your software. So it's very important for you to know flash memory, even though the landing robots on Mars is now using flash memory. But before we talk about flash memory, it's also something important to look at what the modern file system design looks like. So some of you might ask, what kind of file system are we using today in our Linux system? Is it something similar to fast file system, or is it something more similar to log structure file system? The answer is yes and no. So yes, because some extent is similar to fast file system. Some extent of it is similar to log structure file system. No, because both of them, all the existing file systems are either part of the log structure file system, part of the part of the concept from the FFS, but not all of them. So let's look at what the modern file system design looks like. So before we talk about the modern file system design, let's look at the modern file system name, right? If you are running a Linux, your file system is very likely to start with a word like ext, right? And this ext is actually standing for the extend. So what's an extend? So before we start, it's always a good idea to see what's the concept of extend. So as we said, how do we allocate and how do we map disk space? You might remember there are concepts like you can have contiguous allocation. This is like the idea of segments, right? So if you have a file like a.txt, then the a.txt will reside in continuous addresses. So for example, your log structure file system, it follows this way. If you have a a.txt, right, you have to have a free space that's large enough to accommodate all of the a.txt. However, because it's problematic in a way in that it's always difficult to find sufficient amount of external fragment, contiguous space in disk. So garbage collection becomes really important, and you probably have to frequently move data around. So that's an issue of the log structure file system, because you always have to figure out how to make sufficient amount of space for your data in a log, right? And another way which if you think about the idea of inode in fast file system, is actually like the right-hand side. It's a non-contiguous, and the file content can be anywhere, right? So the inode structure, we have a few pointers like this to pointing out what the data are allocated in a space, and is is per block basis, right? So so you have some kind of data structure, a tree structure, like the tree level interaction node to 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 give you the collection of data blocks for this file. So these are two extremes, right? So for log structure file system, it's more like this, and for Unix fast file system, it's more like this. However, as you can imagine, this one has the drawback of object collection, and this one has the drawback of you have limited amount of nodes available for you, and it's also limiting your file size. So both are not good ideas, right? So what are we really doing now is that actually we try to take advantage of this one and also take advantage of this one by introducing the idea of extents. So the idea of extents is that your file is actually resides in several groups of smaller contiguous address, and each of this is called an extent. And you maintain a certain linked list data structure in your inode, or say in your file system structure, to say, well, what's after this extent? So each extent is the data portion of the linked list, and you have a pointer to tell you what's after this. So that's actually the idea of extent-based file system. So in extent file system, right, you can think about if you have a contiguous, like a segment, right, all you need is like a starting address of the size, right? So in your extent-based file system, you can also specify a certain linked list data structure, and each just tell you like what's the starting address of it and how big is the size of the extent and where is the next one. So in this way, if you're lucky enough that you find contiguous space on your hard disk drive, you can still take advantage like log structure file system in a way that everything is sequential, and also you can also get rid of the limitation of limited number of nodes available for you to create pointers to each block, because this is essentially like a linked list, and a linked list can be unlimited size, right? So extent file system help us to get rid of the issue that you cannot always find good enough a good amount of contiguous space for you to allocate a code file, but also take advantage from the linked list data structure in a way that you avoid a limited number of sizes. Right. So so most of the modern file systems, they incorporate the idea of extents. However, that's not just one thing, right? Extent is the idea that modern file system is using. However, they also know that, well, if we want to build a file system that can accommodate supercomputers and also data-intensive workloads and write-intensive workloads, simply one file system is not enough, right? So the modern file system is basically taking some advantage from the fast file system and incorporate the idea of journaling. So the journaling is actually log. So what's the idea of journal is that let me see if I have a slide for this. So, okay, I think I forgot that slide. So, okay, so here is the journaling idea. So the journaling idea in modern file system is that instead of treating the whole file system as a log, I still have a log on my hard disk drive as a buffer for writes. So this is called write ahead log. So you have a log in log area in your hard disk drive. And first of all, when you have a write, you write to the log first. So you have a log structure, you have a log in your file system. And after the log is near a certain threshold, and you start to start to move the log data around to the best place that you think in the rest area in your hard disk drive. So when we write, we first write to a log. So this way, modern file system, they are more like a log structure file system. However, the second time when you move data out of the log and move it to other places in the hard disk drive, then it looks more like a fast file system in a way that you try to address the device characteristic to make sure that they are in the best places. However, because you have a log, so if you have crashes or if you have hardware failure, you can always find your changes in the log. And even though you crashes, you can scan the log first and see if there is any uncommitted change that I made here and apply it to the real data area. So that's the whole idea of log structure file system. Oh, sorry, modern structure file system in a modern file system in a way that, in addition to the management of fast file system, you also have a write-ahead logging. So to give you an idea how modern file system will store your data, let me show you a demo. So here, let me see. I have a demo here. So and you can always find a demo code in a GitHub. Oh, sorry. This is the project code. This is the demo code. Okay, so look at the get-sector.c file that I wrote. The basic idea of the get.c is that I try to create a file, a system call called FIE map. Try to find the file to extend mapping. And when you find this map, it will actually create, it will give you a set of nodes, and each node is actually pointing to an extend. And I am going to dump the starting address, the end address, and the extend. So right now, let me pick a file in my system. So I have a file, let me see. Okay, this one. So saying that I have this file, and this file is 4 gigabytes large. So as we mentioned, right, once you use the disk for a while, it's really hard to find consecutive space. So you can see in the first extent of the file, right, they can only find an extent to store a megabyte of data, and the starting address is this, and the end address this. And then the second extends from an address that's not contiguous from the first extent with slightly larger, with 10 times larger, with an extent that is about 10 times larger, right? And then again, they found another extent, and this time this extent is even larger, and because each extent still has its limitation in size, so they have to break this extent, and a third extent, a fourth extent starts from here, which is contiguous from the previous one with this size. However, this one is only sized like this because you will find from here to here there's another fragment inside, right? So this tells you that, well, for this file, at least in the very beginning pieces, we see one chunk, second chunk, and then another big chunk, right? And your file is basically like a linked list on your disk. So that's how your modern file system will store your data nowadays with the concept of extend. So it's neither log structure file system like, or it's also not fast file system like. And some of you might think about like cylinder group is a good idea. And even with hard disk drive, extend-based file system is not using a cylinder group anymore. Instead they have a block group. And in each block group, they still incorporate the idea that we should have super block, we should have metadata, we should have data together. But again, because you have the write-ahead logging first, so it gives you another layer of optimization to place this data. And this block group would reflect the hardware structure of your hard disk drive. So that's the whole idea of extend file system nowadays in using your disk space. So we are done with the file system on conventional hard disk drive. However, as many of you are aware, a lot of your computer do not have a hard disk drive now. So it's really important for us to see what is flash memory and how the file system should deal with flash memory nowadays. So the first paper that I'm going to talk about is flash-based is NV non-volatile main memory storage system. So I know you have done quite a few research and by reading this paper. So I do want to remind you, what are the characteristics of flash memory? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I definitely see a need for group discussion. So let's go ahead and do it. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, Rogelio, put your hands down. All right, so now let me invite one of the group to raise your hand. Okay, Emmanuel, you got it.
All right, so we're Team Red, and we thought that all of them were correct.
Okay, so where can you find the evidence?
For number one,
What supports you?
there is a chart, figure one.
Mm-hmm.
It
Mm-hmm.
says that read axis is 85 nanoseconds, write axis
Mm-hmm.
is 4 to 10 microseconds. So that's order of
Mm-hmm.
magnitude around 100.
Mm-hmm.
Um, Number two, the granularities of writing and erasing are um, different. I think it's under this effective number of segments. So
Mm-hmm.
smaller segments allow for a cleaner to work with a finer granularity. Writing has to have a much bigger size. Um, it said over there that you cannot, what's it called? Um,
And actually not, right? Looking at the sentence that I put up here, right? Individual bytes can be programmed in 4 to 10 microseconds, but cannot be arbitrarily rewritten until the entire device is erased, which takes about
yes.
15 microseconds, right? So it's actually in the text that's explaining the table,
Okay.
right? So, but this one actually tells you that the granularity of writing and erasing are different. And how
Okay.
about, and this one also tell you the third one, right? Flash memory
Yeah.
cannot be written again without being erased. So how about the fourth one?
Fourth one. The fourth one is correct because they
Mm-hmm,
underestimated NV lifetime. They have a
mm-hmm.
the lifetime is written there said around a million cycles, and then
Okay, and actually, if you look at another pieces of paper that I cited here, right? The program erase cycle is limited.
okay, yeah,
Right. So I am just using the words directly from the paper, right? So be careful next time you guys discuss, right? Although some of you are well, so some of your the places that you observe may well it says something like that, but if you want to find the most precise place, it's actually the place that I'm citing here. But I think you guys must agree that everything here is correct. And it turns out that if you look at this device, right, you will feel like what a is that, right? Like this device seems problematic, right? Writing is a lot slower than reading, and writing and erasing are different, and you cannot erase it for too many times. And in fact, you will know later on. You will know that how few the amount of times you can erase. But for now, like for the four of the statements, every of the statements they are correct. So and for flash memory that we use right now and the time of the flash memory that NV are using right now is actually pretty different. So modern flash memory that we are using is actually the NAND flash technology. And previously in NV, they are using the NOR flash technology. So the biggest difference here is that for modern flash technology, the NAND flash technology, you can read and write in the granularity of pages. And in NV, it's possible to support byte addresses. However, that's no more available for modern solid state drives. And but on the other hand, they all have the write once feature before you erase the blocks in 64 kilobytes or in 64 to 384 pages. So you can only erase the pages in bulk, but you cannot reprogram before or say rewrite before you can erase. So, and another thing which is more problematic is that in NOR Flash, you can only erase a page, a byte for 100,000 times. So 100,000 seems like a lot, right? However, for modern solid state, for modern SSDs, you can only erase the same page for 3,000 times to 10,000 times. And the later the technology, the fewer amount of program erase cycles that you would have. So let me introduce the basic flash memory operations. So flash memories, they are organizing their structure like this. So they organize, their basic unit is a page. And pages, they are grouping in blocks. And each block is the basic unit of erasing, as we just mentioned. And each page is the basic unit of reading. And here I use the white ones to denote the free pages. So saying that well, in the very beginning, right, when there's nothing, I can just start programming and keep programming and programming, right? And although this page, once you program, you cannot reprogram it, but you can read it for many, many times. And the reason is because if you think about the source of how people invented flash memory, they are actually coming from the idea of EEPROM, which is originally a read-only memory, but they happen to know, and sometimes this science and technology is kind of interesting, is that one of the Japanese scientists, they just figure out that, well, by accidentally increase the supply voltage, I found I can reprogram those EEPROM many times, right? So that's how they invent the flash memory technology. But originally their purpose is read. So once you programmed, you could read it many times. That's its original design purpose, right? And when you program them, and when you program them for a while, it's hard to find free space. So it turns out that you have to erase a block. And when you erase a block, you will have the capability of reprogramming those pages again, right? So in modern market, you will be able to find a lot of different types of flash chips. And if you are buying an SSD, it's very likely you are going to have a TLC or QLC chip. But what's a TLC and QLC? And because they are overly complicated, so here I just use a similar idea called MLC, multi-level cell, to tell you what's the idea of TLC and QLC. So in most of the memory devices, as you guys know, right, we usually just have one cell store one bit of data. It's either zeros or ones. However, we found that the density is too low in this way, so we want to lower the cost. And some of the engineer, they are really smart in a way that they find that, well, if we can design our sense amplifier in a certain way, then we are able to distinguish different voltage level within the 1 and different voltage level within the 0. So it turns out that you can use a single cell to store multi-levels of voltage. So it turns out that if you can divide them into 4 different voltage levels, you are able to store 2 bits of data. And if you are able to divide them into 8 different voltage level, you are able to store 3 bits of data within the same cell. And because you are able to store 3 bits of data in the same cell, so that's why they call it triple. And quad label is because you can store 4 bits of data within the same cell. However, if you are going to program your bit data into this bits serially, is pretty slow. So what would happen nowadays is that when we are programming the MLC cells, instead of treating a single cell to store consecutive data, we actually separate the storage of 2 bytes in a way that we treat the first, the high-level bits as 1 page, and the second parts of the bits as a second page. So when you program, you are actually programming your data in a way that, am I getting the right slide for this one? Okay, so this one is the right one, right? So you are treating your data in two different pages, into two different pages. The higher level bits is considered as the first page, and the lower order bits is considered as the second order bits. So saying that if I have a data with bit sequence like this, instead of the first time you have to, so for example, if here I have data like 00, right? I have to if I don't treat this pages separately, I have to program this cell all the way to the end, right? However, if you can treat the page the data into different pages, the first time when the first phase of the programming, you only need to like move the data either from here to here, or just don't move. So your program will be a lot faster. So for example, here I saw the first bit is 0, right? So you can just put the data here instead of putting them to the end, right? So so in this example, those ones I just stay them at the same space, and in the first time when I'm programming, I just need to move those zeros to 01, the position of 01. But because I know that the second page is not used at this point, so when I read 01, I know this is the content of the first page, and the first page should be 1, right? 0, right? And if I have a second part of data that I want to program, then I can move another part of I can just move the label down by 1 in a way like this. So when I read this, I still read the first page data as ones or zeros, and the second part as the original as what they should be in this way, right? But in terms of programming, it's a lot faster. So it's okay that you don't understand this, but as you can see, right, when you are reading the first page, it's really quick because you only need to separate your data into two different levels. And when you are programming the first page, it's also very quick because you only need to move at most 2 levels, right? So it turns out that even with multi-level cells, even we mentioned that for the program performance is different from the read performance, but even the read performance has a lot of difference. Like for this one, you can see for read performance is not uniform. The variance is very large, and for write is even worse. The worst case could be like 2 milliseconds, but it could also be as fast as like 250 milliseconds. So microseconds, right? In this case, and for erase, it's always slows. It slows in a way that it takes multiple milliseconds to erase. So that's the flash performance. But as you can see, write has a lot of difference because as I just showed you, when you program the first page and when you program the second page, the algorithm is completely different, and the distance of moving your cell is also different. So that's why programming takes a lot of time. So yeah, and another thing is that if you look at the program erase cycles that we have in modern flash memories, right? So for SLC, you can get like 100,000 program and erase cycles. And when you move to MLC, it's 5,000 program and erase cycles. When you are using a TLC, it's only about 1,500. So which means that if you have a solid state drive, if you try to rewrite the same place for 15,000 times, your solid state drive will be dead. So that's the issue. And it's and if you read about this chart, right? This is from Micron, one of the biggest flash memory vendor. And as you can see, is that, well, although QLC will give you very good capacity, however, the program erase cycle right now, every QLC cell can only be reprogrammed for at most 1,000 times, and a lot of low quality ones, they can only be programmed for 800 times. So you really have to design your file system carefully for this kind of devices, because thinking about that, you can only reprogram the same place for 800 times, right? So so thinking about that, right? If we leverage the same abstraction that we have, and what happens inside the SSD is that because we have to use this space carefully, right? So when you are writing data to the SSD, your CPU will issue the commands to the SSD controller, and the SSD controller will have to figure out what's the best place to perform this update. And if you have conventional solid state drive, if you have conventional hard disk drive algorithm, what you would be thinking is that, well, if I am updating 0, right, then, well, this is block 0, this is the zeros place, then I erase the whole block. And because we cannot write page 0 directly, right? So if you are using the conventional way that you deal with the hard disk drive, then what you will be thinking is that let's erase the whole zeros block, so that, and copy the data of page 1 and page 2 out of the block and rewrite them all the back again, right? So if you treat your data like this, then data access like this, then in QLC technology, once you write the same address for 800 times, this block is dead, right? That's one thing. And the other thing is that if you think about the latency, it's also bad, right? So reading each page would take 30 microseconds, and writing them back would take 2 milliseconds, and erase would take 3 milliseconds, and you will get 9 milliseconds if you do things in this way. So it turns out that your performance is not even faster than hard disk drive, right? So this is definitely not the way how we should deal with flash memory. So so far we learned one thing, is that writes are problematic in flash. So how do we solve this problem? And as we learned in computer science, is that, well, all problems in computer science can be solved by another level of interaction. So what's the interaction that we add to accommodate solid state drive? So we still want to maintain the same stack. So the only place that we can add an interaction without affecting your software system stack, and computer architects, they are such a good group of people, is that they are always nice. They are very good in a way that they hope the software programmer never have to modify their code. So we create something called flash translation layer inside the SSD. Try to dynamically remap your writes to the best place and maximize the lifetime of your solid state drive. So if you are such a good computer architect, and if you want to create an internal layer called flash translation layer, try to remap your data content to maximize the write performance and maximize the write lifetime of your solid state drive. How many of the following do you think are good practices? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, for this question, I am requesting you guys to have a 2-minute discussion real quick. Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it's kind of interesting that after discussion, I saw some changes. So I'm inviting one of the group to share your thoughts with us. Okay, so I have Rogelio. So what do you think?
Well, our group thought 1 and 2 are correct.
Okay, so 1 and 2 are correct.
Yeah, we didn't reach a full agreement though.
Okay, so why
part,
don't you guys with not agreeing with 3 and 4?
For 3, we weren't really sure.
Okay.
For 4.
So how about the glue team? What do you guys think? Can some representative from the blue team tell us what do you guys think? Okay, Xingyun.
I think 1, 2, 3 are correct.
1, 2, 3 are correct. So why do you agree with the third one?
If your firmware on the SSD could pre-allocate the, I mean, you need to write the flash average to make the lifetime is longer. So if you do this thing before you write, I think it could get a better performance.
So where did you learn that pre-allocation locations will give you better performance? Which paper you learned about this?
Just my personal idea.
Okay, so but
no
if I
reference.
want to ask you about which paper you learned about this, which paper would you say?
I don't know.
Okay, can anyone tell me about that?
Maybe the Envy paper?
No. You have read this paper before. Okay, so if you look at this, right? So think about this, right? Like, first of all, right? Why we want DRAM buffers? Why we want write asynchronously, right? Because it will improve the performance, and we also need DRAM buffers for that. And out of place update, it avoid time-consuming read erase, right? Pre-allocation, so you have a free list and garbage collection when a free list is low, and why not aggregate writes? Because let's say the force aside, right? But if you see 1, 2, 3, and 1, 2, and 3, what file system you learned so far has all these characteristics? Can some of you tell me about that? What file system you learned so far has the characteristic of 1, 2, 3? Raise your hand. Tell me. You learned this before, right? Which paper does asynchronous write? Which paper, when you have a new version of the data, you are not going to update it in the same place? Which paper, when you write, you always have a place to write? Can some of you raise your hand? Okay, so Emmanuel, which paper?
Log file systems.
Yeah, log structure file system,
Yeah,
right?
log
So the characteristic is actually log structure file system. The only thing that we didn't do is that we don't aggregate write to the same bank and chip. And the main reason is because flash memory is different from conventional hard disk drive in a way that the conventional hard disk drive have only one disk head. However, flash memory, you have multiple chips, you have multiple banks, you have multiple blocks, and they can potentially be accessed together at the same time. So if you try to aggregate writes to the same bank and chip, you are going to sacrifice the parallelism, and it's actually bad for performance, right? So that's why that's how we should deal with solid state drive. But except for the last one, everything is similar to log structure file system, right? So this is exactly how flash translation layers should work, right? Because we are always lazy to modify our application. So flash translation layer, it builds a log structure file system inside your solid state drive to maximize your lifetime, to maximize your write performance, to accommodate the slow writes, right? And as a result, if you look at your solid state drive, they actually have a pretty powerful processor. So even the consumer level Samsung SSD, you have 3 cores ARM processor inside your solid state drive, just because you want to maintain this log structure file system. So with this log structure file system inside the solid state drive, when your solid state drive receive a read request, well, we have a mapping table to tell you which block, which page has your data. However, when you are trying to write to an address, instead of rewriting to the same block, the same page that your original data location, we just append it to the end of the free space, the beginning of the free space, or the end of the allocated space, right? So this manner is very similar to log structure file system, and you just invalidate the original copy, right? So this is exactly like what the log structure file system is doing. And whenever you are out of or you are low on free pages, we will have to perform garbage collection. So for example, you use some of the algorithm to figure out which block contains the most invalid number of pages. So for example, like when we try to write a new data, we figure out that, well, we are running out of free pages. And what will happen is that you will first use your DRAM buffer to copy the live data of the target block that you want to erase. And you copy those data out, erase the whole block, and write the valid data back to the block, and then you can finally perform the writes. And when you perform the writes, see, you still write to the end of the allocated space, or say the beginning of the allocated space. So it's exactly like appending to the end of the lock. So the flash translation layer is exactly like a log structure file system. Of course, they have they have garbage collection, and it's also similar to log structure file system. And also, but however, because the flash memory has limited amount of lifetime, so you also have to have a lot of algorithms to take care of making sure that the wearing of each chip must be fair enough. So those are what's happening in a flash translation layer. However, it's exactly like the log structure file system, and this is exactly how Envy works. And it's actually an internal file system of flash memory, which is transparent to your software, so that you don't have to modify your software. And it works exactly like the log structure file system in a way that it proposed transparent in-place update is that it exposed a block address to your software, but internally it has a mapping between the block address and the page block inside the SSD. And how it uses this space is exactly like a log structure file system. So you need to have a lot of caching, you need to have buffering, you need to have garbage collection. So that's the whole idea. And as you can imagine, a lot of you have the bad habit that, well, if I have an SSD, I want to put as many data as possible inside the SSD. What you should see from this paper is that if you try to use the flash storage for more than 70%, you start to see the throughput becomes really slow. So a lot of you were saying that, well, I have a USB thumbstick in the very beginning, it works really fast, or I have a solid state drive, it works very well in the very beginning, but when I start to use it for a while, it's getting slower. Sir, it's just because you put too many data inside, and the utilization of your flash array is getting larger, and you have a lot of invalidated copy of your data. So you are getting slower because of this. And this paper tells you about this, right? And because you have a lot FTL algorithm, so your solid state drive today still runs an internal file system like Envy, and you use the DRAM to store the mapping table, to buffer your data, and use the processor to perform FTL algorithms. So that's how your solid state drive works. So now I am inviting you to think about this, right? As we mentioned, the reason why we want to know the architectural features of your hardware is because we want to know what's the right way of designing our system. So looking at this question, can you tell me how many of the features that we have in existing file systems should we keep if we are in the era of flash memory? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I'm inviting you guys to have a group discussion real quick. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I'm inviting a group to share your thoughts with us. Okay, Rogelio, what does your group think?
We chose 3. D is the answer. 2, 3, and 4.
Why?
1 makes no sense. There's no disk. 2, larger
Okay,
block
so there's
size.
no cylinder.
Yes.
Why larger block size is a good idea?
I think it's to me. Well, I think we agreed it was something. It sounds like something that we would want.
Okay, so the next time,
files.
if you guys are answering questions, right, make sure that you have prepared well why the reason is that, right? Otherwise, is not really insightful, right? So, how about fragments?
Fragments, yes. Essentially, if we think about files as a linked list, then I think they're stored in separate areas of the storage device, and then logs.
Okay.
We just had a conversation about logs. We definitely want that.
Can I invite a blue team to share me with your thoughts, to share with us about your thoughts? Okay, Xingyun, what do you think?
I think 234 is right. The larger block size can improve the reading performance, and the fragments could, when we erase some blocks, the fragments could make our lifetime longer because you don't need to erase some unessential error.
What's fragments?
Fragments divide some block into a smaller.
Why is that a better idea?
Spaces. Yeah, for example, if you don't have for SSD, I think if you don't have fragments, you need to erase a whole block in some time. But if you have fragments, you can erase a fragment, maybe not whole.
I don't get it.
If the file,
from my perspective, right, I think large block size is good, as you mentioned, right? You can improve the read performance. And the other thing is that large block size may be a good idea, right? As long as the block size, well, here the block size is different from the block of your flash memory, right? So block of the flash memory, that's a hardware structure, but the block size is the file system granularity, right? So as long as your block size is larger than your page size, right? Or you should just make your block size to be the same as your page size, then your management would be pretty good, right? And for fragments, right, I don't think it makes sense in a way that flash memory can only be written in units of pages, right? So smaller granularity actually doesn't make sense because thinking about that, you cannot program per byte anymore, right? And the reason why the hard disk drive, they want fragments is because you are still able to do partial programming within your block, and you are able to do in-place update, right? However, that's not the case for flash memory, so I don't think the idea of fragments works. And none of you chose logs, right? But actually, that's a very interesting idea because flash memory itself already have logs. Do we still need logs in flash memory? So so now let's look at the paper. Don't stack your log on my log. It's actually one of my favorite papers throughout this quarter. So a lot of you, as I can tell from the previous 70 minutes from our conversation, I don't feel like a lot of you really understand the concept of log. However, log is really important, right? So if you haven't touched my class, this is probably your first impression about log. And when you see the title of log on log, this is probably you think, right? And if you are in a mathematical background, this is probably the log on log that you think. But what really a log is? So log is actually a universal name for a data structure that is append only, and the data structure can record all changes. So thinking about that, right? Every time when we say we want to debug, we have to use a log. We have to look at the log. The log is actually a file that contains all the changes you have, and they are sequential. And whenever you have new changes, new events, you just append it to the end. So that's a log. And the log structure file system exactly like this, because every time when you have a change, you just append your changes to the end of the log. So the concept of log is a very universal concept in computer science, in a way that any data structure that is append only and that you use to record all changes can be called as log. And why everybody likes the data structure called log? Because it gives you better performance, right? Because always sequential access, because all you need to do is to append to the end, and it's sequential. And it's quick for writes because you don't have to sanitize existing data first, right? And it's also good for recovery because you can see all your previous change in the log. However, as we later see, right, the log has its issue of garbage collections, because if you want to maintain the sequential space of the log, you have to move data around. So this is the issue of the log. So, but however, as we mentioned, log is such a good idea. So log is actually everywhere in your system. So if you are familiar with database, no matter what kind of database system that you are using, the NoSQL database, the big table, or even the conventional SQL databases, they all have something called log to record all the transactions in a database. And in a file system, as we just mentioned, if you are using ext file systems, you have a write-ahead logging in your file system. And then for flash translation layer, it's also log structures. So if you are running a database system in a computer, then turns out that you are going to have triple layers of logs. So what happens if you have triple layers of logs? So thinking about that, right? If I, let's not talking about the 3 level. Let's look at the 2 level. Saying that I have a log structure file system, and the log structure file system, it allocate a logic block address exposed by the SSD like this. So I thought I have a sequential address space, and this will be used as a log. And this is my current allocation of the log. I have some invalidated space, and I have some free space. And now, saying that, I want to, so the SSD wants to figure out that I only have 4 pages remaining, so I want to do garbage collection. So the SSD does a garbage collection, move the ABF to the end of the log, and then you got a new block for you to use. On the other hand, the file system also feel that I need some more space. So turns out that I want to move ABF to the end, and so that I can free up this space for my log. So what would happen is that, well, the file system, it will invalidate the logic block address of the original ABF. So turns out what would happen is that the file system will write ABF here and try to invalidate the original copy of ABF, and then write ABF again to the SSD because they are moved to the new location, ignoring the fact that the ABF are still valid somewhere in the SSD. So turns out that the ABF, they got rewritten at least twice in the system, because the file system has its own garbage collection, and solid state drive has its own garbage collection, and they are not coordinated. And we just mentioned that write is a really bad thing for solid state drive's lifetime, right? So So this gives you an idea that sometimes adding another label of interaction is not a good idea. Um, and log on log is exactly a problem that you have too many layers of interaction. So for logs, I would put a question mark here. And in fact, I don't think it's a perfect idea. And in fact, there are many examples. And even though this one I just read this morning. So first of all, 4 years ago, Spotify has been involved in a group lawsuit about Spotify's engineer. They don't know the characteristic of solid state drive. So they keep writing your data into a log in your solid state drive and kills everybody's iPhone who has a Spotify. So so sometimes as a software engineer, you don't think you need to know the underlying hardware components. The answer is no, because like the idea of Spotify, it actually get themselves into trouble because of their software engineer doesn't know how to use flash memory correctly. And recently, I just 4 hours ago today, and actually this morning, I just saw that Apple also have an issue that their latest M1 Max, the Big Sur, the most problematic version of Mac OS ever, they actually try to write your virtual memory files in swap files intentionally on the SSD and can kill your M1 Mac super quick. So those are the examples that why I am spending the whole lecture to teaching you this interesting characteristic about the flash memory and why we should care about the log on log issue. So how to solve the log on log issue? A paper that I have published in 2017 actually give you an idea that, well, if you can change your storage interface to not use this the blocking interface. So for example, if you know ahead of time that, well, if you can make your hardware software interface or say your solid state drive interface to be more aligned with modern applications. For example, we know a lot of applications right now, they love the idea of key value store. Then what if we can expose a key value interface to the software, and it turns out that your file system or your database system no need to maintain its own log. So it turns out that you only have one log within the system without this multiple layers of log. And if you are interested, you can definitely read a paper. And before you leave the classroom, there are a few things that I want to let you know. So we still have a reading quiz due this Thursday. And the office hour is now Monday, Thursday. And make sure that you use the office hour Zoom link. And Piazza is the most effective way. But if you find bug, I think putting it on GitHub, it would be a good idea. Project due March the 2nd, no late submission is allowed. And just a commercial, because I'm teaching a quantum computing and computer architecture class in the next quarter, but the enrollment is pretty low at this point, and I really want to make this class happen. So if you need a course if you need a course, then you can consider EE 260, and it's going to be a seminar style course. You only need to present once in a quarter, and at the end of the quarter, you need to write 2-page research proposal. I guarantee there won't be any reading quizzes like this quarter, and there will not be any midterm and final for that class. So if you want a course, and if you are interested about the idea of quantum computing, maybe considering enroll in this class. Other than that, enjoy the rest of the night, and I will see you this Thursday.